everybody, and welcome back to Unit 4, Lesson 4, which is an introduction to the idea of related rates. There are two learning targets for today. So today we're going to learn how to apply the chain rule in order to differentiate variables in a related rates problem with respect to time. And the second learning target is we are going to use a combination of differentiation rules, including the product and quotient rule, to differentiate when necessary. So you've got to kind of go back and review and remember all those derivative rules. Now, when we're talking about related rates, this is the second application of derivatives that we're going to talk about in this unit. The first application was the idea of particle motion and examining an object that is moving. The second idea is the idea of a related rates equation. So imagine you are inflating a balloon. Describe the different quantities that are changing over time while the balloon, this should say balloon, I apologize, while the balloon is being filled. If we're inflating a balloon and we use kind of our imagination, several things are changing. The radius of the balloon is going to change with respect to time. The surface area of the balloon is going to change with respect to time. The volume of the balloon is going to change with respect to time. So there are lots of different things changing here. How the radius of the balloon, how much surface is covered by the latex of the balloon, the volume of air that's contained within the balloon are all changing with respect to time. Now imagine you're filling a cylindrical cup of water. What different quantities are changing over time when this cup is being filled? Well, in this case, when we look at this diagram, you can see the radius of this cup is not going to change. So like this radius is a set quantity. The cup isn't going to expand. However, the height of the water over time is going to change. How much water is actually in the cup. So the volume of the water over time is going to change. And I do want to make a special note here that in this case, the radius doesn't change. When we are analyzing a scenario where multiple quantities are all changing with respect to time, so in this case, radius, surface area, volume, just to name a few, in this case, height or volume, to name a few, we say that we have a related rates problem because although the radius is not changing at the same rate as the surface area, the rate at which those things are changing are related to each other because they affect each other. When the radius gets bigger, the surface area is going to get bigger. When we tackle these scenarios, it's very important to read carefully and use correct notation to organize your information that you know and then use that information to find your missing values. So we're going to be reading complicated, kind of wordy scenarios, and it's going to be really important to make sure that you organize your work and show your work neatly to keep track of all of the lots of information that you're given in the instructions. Today, what we're going to do is we're going to practice just reading and finding information. So first, we're going to read these statements carefully, and then we're going to write down whatever information we can find using correct calculus notation. So the first thing says the volume of a sphere is increasing at a rate of 8 cubic inches per second. Now this says the volume of a sphere is increasing at a rate of 8 cubic inches per second. So we're talking about the derivative or the rate of change of the volume with respect to time because it says per second. To show this using notation, we would say dV over dt. So the rate, the derivative of the volume with respect to time would be equal to 8 cubic inches, we would write inches cubed per second. For problem number 2, it says the depth of water in a well is decreasing at a rate of 10 inches per minute. So the depth of water in a well is decreasing at a rate of 10 inches per minute. Again, this is a rate, so we're talking about a derivative. So the derivative of the depth of the water with respect to time, because it says inches per minute, would be equal to, now this says it's decreasing at 10 inches per minute. So I'm going to make that a negative 10 to show that it's decreasing. inches per minute. This piece right here, where you realize that this has to be a negative rate, is key because that is one of the ways that you have to really read carefully. It's not going to necessarily say -10. You might have to read really carefully and see that it's decreasing. The distance between two cars traveling on the highway is increasing at a rate of 3 meters per minute. So the distance is increasing at a rate of 3 meters per minute. So it's the derivative of the distance with respect to time. So I would say d for distance over dt would be equal to 3 meters per minute. Now in this problem, since I'm increasing my distance, the distance is increasing at that rate, it's a positive rate. For problem number 4, it says the amount of gravel in a processing plant, so the amount of gravel is decreasing at a rate of 4 cubic tons per hour, with respect to time. So the amount of gravel, so dA over dt is equal to, since it's decreasing, we would say -4. Cubic tons means tons cubed per hour. Next, we're going to say the radius of a sphere is expanding at a rate of 12 inches per minute. So the radius of a sphere, R, is expanding, so it's getting bigger, at a rate of 12 inches per minute. And at this time, R is equal to 5 inches. So now we have two pieces of information here. First, we know that the radius of a sphere is expanding at that rate. So dr over dt is equal to 12 inches per minute. And we also know that at that time, R is equal to 5 inches. So we also have the information that R is 5 inches. Now we have two given pieces of information. We need to find both of those and organize them, write them down neatly. And last but not least, when a tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. So we're talking about a tree that's 50 meters tall, and the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. So the tree is 50 meters tall. So I would say that the height of the tree is 50 meters. And I also see that it says here the diameter is increasing at a rate of 0.03 meters per year. So the rate of change of the diameter with respect to time would equal 0.03 meters per year. And I'm going to show that using notation. Okay, as you can see, reading carefully here is really key. Really taking your time, underlining key information, and listing it out neatly, including using correct units, is really key here. The other key to being successful in a related rates problem is to be able to take the derivative with respect to time. So you will notice that all of these derivatives are with respect to time. The rate of volume with respect to time, rate of change of depth with respect to time, rate of change of distance with respect to time, they're all dt. What that means is that when we find these derivatives, they should always be with respect to time, and every variable is changing at its own rate. So here's what we have to do. If I want to take the derivative of this with respect to time, I would start with the derivative of volume. So the derivative of volume with respect to time, I can show using the notation dv over dt is equal to, now s cubed, so I'm gonna assume here that s is changing also with respect to time because that's how it's going to be in a related rates problem. The derivative of s cubed would be 3s squared. But then since s is also changing, I need to multiply by ds over dt. This right here is the chain rule. So we took the derivative of the outside, the cubed, and then the derivative of the inside, the s, we represent using ds over dt. What that means is in these problems, for every variable that you take the derivative of, you always have to do the chain rule because it's always changing with respect to time for each of those variables. They each get their own chain. For number 8, I would take the derivative of c, so I would say dc over dt is equal to, now 2 pi is just a number, so I'm just going to copy the 2 pi. And then the derivative of r would just be dr over dt. Because there is no like outside function there, it would just be times dr over dt to represent the derivative of r. For problem number 9, you can see we're actually going to have to use product rule because we have L times W. So we're going to have dA over dt is equal to, now product rule says copy the first, so L, take the derivative of the second, so times dW over dt to show the derivative of W, plus copy the second, so I'm just going to copy the W, times the derivative of the first. So I'm going to write down dl over dt to represent the derivative of L. Last but not least, in a problem like number 10, the derivative of x squared would be 2x times dx over dt, the chain rule, or the derivative of x, plus the derivative of y squared would be 2y times dy over dt, because y is also changing. It gets its own rate of change, its own derivative, equals, and the derivative of 25 is just 0. So the derivative of 25 would just be a 0 here. Okay, that is it for today. Thank you guys so much for watching, and I will see you soon for some practice.